call it reduction. But actually reduction always happens together with the oxidation together as a pair, right? So then which one is reduced? The organic molecule is reduced, right? Then which one is oxidized? Do you remember the reaction? Hydrogen was oxidized. Right? Originally H0 changed into H plus, that was oxidized. What is the role of PD? It's a catalyst. It is not changing. So oxidation reduction happened together. This reaction, our main interest lies in the organic molecule. That's why we call it reduction. And that is kind of an addition reaction. Right? Two hydrogen was added. Elimination is the opposite reaction. If you remove two hydrogen, making double bond, then we call it elimination. Substitution is a changing. One coming in, one moving out. That's a substitution. Okay. It's kind of addition, but we don't call it hydrophobic or hydrophilic here. And this is not elimination, that's addition reaction. Hydroxylation means one OH and maybe the other side, maybe the proton, or OH, two hydroxyl group added. That's a hydroxylation. Hydroxyl means OH or the water. Okay, that's hydroxylation. Hydrogenation is hydrogen is added. That's hydrogenation. 이거는 제가 보면 Okay, let's check. This reaction was reagent was a hydrogen molecule. And we use metal catalyst. It can be powder or activated. Activated means its surface area was increased. But anyway, metal surface here. And this reagent come together to this surface, and we believe this bond is cleaved here equally. If I draw the arrow like this, that means the one electron is removed. Then this bond, this hydrogen bond becomes weaker, and it forms hydrogen atom or hydrogen radical. Proton is, if this is heterolytically cleaved, like this, then this side becomes proton, the other side becomes hydride. Okay. But in this reaction, this is a homolytically cleaved. It generates H dot, and it is added to double bond to this 1 electron side. Going together. Okay, so this is usually the mechanism we draw for this reaction. So then, if these two hydrogen from hydrogen molecule go together, then usually that may go into the same side of the double bond. That same side addition we call syn addition. If it is opposite, one goes here, the other goes from the other side, we call it anti-addition. This kind of thing we have learned. So this hydrogenation reaction is equally broken and then go into the same side. So usually this reaction is non-polar addition. Polar addition means somehow this is one side is shifted and this is a are going to learn a little different reaction today. That's why I wanted to compare these reactions. So let's see what you say. Proton was not formed in this reaction. Okay. Hydride was not formed either. This is equally fluid. And generate, we could say hydrogen atom or hydrogen radical. Reagent wise, you could say hydrogen molecule, but my question was what is a reactive intermediate? After reacted with the metal surface, it is broken into the same species. Okay? Yeah. Previous reaction was isolated double bond. It could be hydrogenated or reduced by palladium, but this reaction was the benzene ring was reduced. You need much stronger catalyst. So that reagent was either platinum or rhodium activated on carbon. So those were a little different. You needed to control those reactivity. If you use the same reagent from previous reaction with a Steiner-like structure, like this, if you use this reagent, what product do you expect? Do you expect this product? That is even stronger one, you may expect fully reduced this product. Okay? So that is to control your reactivity. Palladium is a little less reactive than platinum or rhodium. Okay? So there was some reaction we had learned the last class. 재미를 볼까? 영수가 있던 영수 있어? 벌써? 재미를 주는 거 나가도 후야. Sorry. Okay. So let's move to your class. Okay. Today. We are in chapter 17, new chapter we start. And this chapter we are going to study about alcohol and phenol, which may be quite familiar to you. You know what is alcohol. And alcohol, if we divide into different structure, alcohol can be alkyl alcohol or phenyl alcohol. So phenyl or all together we call aryl. So if it is a specific phenyl, no substitutions at all, we call this a phenol. And another in the intermediate structure by anol. Anol can change its structure very quickly to other forms. Can you guess what is the other form of this anol? Assuming that this all position is a carbon. What do you expect? Ketone. And can you give the name of the ketone? So let's say this is all carbon like this. This is the N, alkane's N. This is all of alcohol. So that's why we call this an anol. Okay. This is kind of a unstable intermediate in many cases, and it can move, this electron can move like this, and actually this is catching up to this proton. This forms this structure, this is ketone form. Now what is the relationship of these two materials? Who said that? What is a tautomerization? Okay, let's assume that we don't know the term tautomerization. Other term? A little more general term? Oxidation? 새로운 얘기는 나오네. This reaction is oxidation. Is it oxidized. Let's think about the oxygen. Okay? Oxygen's the oxidation number of this guy. What's the oxidation number? Oxygen molecule's oxidation number is 0, right? All other stable oxygen species usually they are -2, right? And that oxygen, what is it? That was -2. Because this is more electronegative than proton, more electronegative than carbon. Oxidation number 2, correct? And how about this oxygen? Same thing. Oxidation number of oxygen was not changed. And let's check the carbon. This carbon, let's check. This is the most the vulnerable carbon. And that carbon's oxidation number. Carbon-carbon connected 0, carbon-carbon 0, carbon oxygen plus 1. How about this one? This is plus 2. This is plus 2. Yeah, that is really oxidized. Then which one is reduced? Maybe this carbon is reduced. That one, for now, 0. This one, -1. Yeah. Technically speaking, there is some oxidation reduction happened if you count this carbon character. A little change it. But altogether, if you sum it up, this is +1, this is +1. So altogether, the total oxidation status is not changing. So usually we don't call that as oxidation reduction. So that carbon center wise, 이런 거 해보면 한번 쳤는데, it looks like there was some shifted of electron. The density was changed. That's interesting observation, but we don't usually call this oxidation reduction. Then, the relationship between these two. Is that resonance? It's not? Then, that's isomer. That's isomer. If this is an isomer between two, then if they are moving very quickly between them, we draw this double arrow. This is equilibrium, right? This equilibrium and resonance is this notation, right? Then this is a good chance to think about what's the difference between equilibrium and resonance. What's the difference? How do you distinguish which one is resonance, which one is equilibrium? Okay, go ahead. Okay, one definition can be in resonance, there's only existing in the intermediate status. But in equilibrium, there's isolated form here and here. That's good definition. By looking at those structure, another technical other way to look at which one is resonance, which one is isomer. Some isomers they are very stable, even they are not in equilibrium. Right? It's totally different structure. In this case, it's quite fast moving between two, so that's kind of an equilibrium. We can recognize the speed of the equilibrium. In resonance, which one is moving? Only electron is moving. In isomer or isomerization, some atom is moving. In this case, which atom that has moved? Proton is moved. In that case, the proton's oxidation number is always a +1, so we can call it proton. Only proton is moving, then proton is the lightest atom, right? That's why that movement can be much quicker than carbon movement. That's why this is special, very fast moving isomer we call special name as a photomer. This is what Hannah said. Photomer and that relationship among the isomerization, this is a special isomerization. And This is called as a tautomerization or tautomer. Okay. So most important thing when you look at those relationships, then when you draw those arrows, whether you draw this one or this one, okay. Sometimes if you draw the reaction, you draw this way, right? This is a reaction. And if you draw this way, what does this mean? If you write your experimental lab notebook, if you draw this way, what does this mean? I designed this reaction, but actually the reaction did not finish, or the reaction didn't happen. Okay? This is what it means. And it forms, if you draw like this, what does this mean? This is unisolated, or just a detectable, but not isolated intermediate. What does this mean? This is imaginary transition state. Transition state is even, it's not detectable. Intermediate sometimes are isolatable or at least detectable. Okay? So if you draw reaction profile, this is intermediate. This is a transient state. Sometimes we put this number here too. This is a reactant and this is a product. Okay? So this is good example for this. That's why they put this kind of bracket here. This is kind of unstable or short lifetime of the material, like intermediate. It can form this temporarily, but it does not. Usually it's difficult to isolate the dispose. Usually ketone form is a little more stable. Then we draw this arrow like this. Long arrow and short arrow. Okay. That means this is more stable than this arrow. Okay, this is some general form of alcohol. So that means the alcohol, mainly alkyl alcohol or aryl alcohol. And then if it's the alkyl alcohol, depending on the carbon number directly attached to hydroxyl, and we call this, if it's 1, then this is primary alcohol. And if it's 2 alkyl group, secondary alcohol, and 3 tertiary alcohol. When I was a student, long time ago, there's many different names. 1차, 2차, 3차 알코올, 1도 알코올, 1급 알코올, 하나 있습니다. 1도 알코올, 1차 알코올, 1급 알코올. So those terms now these days not much used, but still very okay. 1급 alcohol. Seems like for now we don't use many of these, but these two terms. This is exactly 1차 alcohol is a primary, secondary, tertiary alcohol. If the hydroxyl group is 1, then 1급 alcohol. In English, what do we say? Maybe mono alcohol, dialcohol, trialcohol. Specifically, this is ethanol. This is glycol, ethylene glycol. This is glycol. This is a common name, not a balloon. But anyway, these terms we don't use much for now. But this term is what we are using: primary, secondary, tertiary alcohols. Depending on those structures, the reaction is a little different. So that's the thing we may have to look at. Now, let's think about the organic molecule. Alcohol is somehow it has a hydroxyl group on the organic molecule. The simplest organic molecule, what do you think? Carbon and hydrogen. Okay? What is the most abundant organic material on the Earth? We said only the carbon on the crust, on the surface of the Earth, only 0.2%. But we chose the carbon as life molecules. Our main body, except the water, carbon-centered material is our central molecules. And to sustain our body, if you think about the food we take, can you think of any non-organic material we take? Water and some of the minerals, but it's very minor, supporting materials or nutrient or calories. But main material, if you think about any drinking, eating materials, anything you can find a non-organic. Almost all the materials we take. Some materials are just a pass through, so we don't count. They are just a guest. If they they are incorporated into our body. Everything is organic. And who make those organic molecules? they are made by lipoforms, other lipoforms. So those are the organic material on Earth, maybe the crude oil, maybe the main source of organic molecules among life. And those crude oils, we believe that these are also originally formed as organic molecules by some lipoforms for a long time. And then they are pressed with a high pressure and high temperature. They lost all other heteroatoms. Those are maybe mainly oxygen and nitrogen, or sometimes the phosphorus and sulfur. Those materials are all removed. And simplified form is most stable, and then they are kept under the earth. They are the crude oil. If it goes further, maybe even they lose this hydrogen. They become carbon, charcoal, sometimes. Even they are not organic. We don't call it just a carbon as organic, but they are origin-wise, they are also maybe most likely they are originated from organic material. If not, it may be very difficult to accumulate to carbon this concentration. Okay? So in a sense, this is maybe most abundant organic molecule, and in a sense, this material is very useful material if you can eat them. But we cannot eat them, and our body is based on carbon, and we always think maybe this is one side of the material, and the other side of the material is water. Right? Water is also an amazing molecule. It's a very common molecule, so we don't think much. But water, we just usually H2O, but when they are in the bulk of the water, always they exchange this hydrogen with each other molecules. So, in a sense, this is a big polymer structure or network structure, because this is not stable H2O unless they are vapor in the air. They're always connected together, and then exchanging this hydrogen and making extra interaction, so-called hydrogen bond. And in pH 7, we know it's 10 to the minus 7.1 molar, 0.1 micromolar concentration of H plus, and same concentration of OH minus, they exist all the time. It's very dynamic structure. And this structure has distributed charges. Oxygen has more negative charges, hydrogen has more positive charges. So these separated charges generate partial charges, plus and minus. If it is a 2, then we call it dipole. If it's a 4, quadrupole. Anyway, if there is charge separation, non-neutral, then we call this property as a polar. That polar means charge is partially distributed to one direction, and it's non-neutral. Partial positive, partial negative forming, that's polar. Right? So all this together, these two molecules, usually in organic chemistry, we manage those molecules in the lab. And usually we use this kind of technique, so-called extraction. Assuming that those are two main characters, those materials. One molecule is organic, the other molecule is aqueous, water-based. And these materials, depending on their intensity, sometimes organic can go up, sometimes organic can go down. But one side we call polar, and the other side non-polar, or sometimes we call this hydrophobic or hydrophilic. Right? Seems like this is divided the whole world into this only two, but actually the world is not so simple. Even there is the similar structure to hydrocarbon. If you exchange this H with a fluorine, okay, the structure-wise is very similar. Size of fluorine is very small. Size-wise also is a similar size of the proton, but charge separation is different. Electronegativity of carbon. electronegativity of carbon. 2.5 좋아. Hydrogen 2.1. Fluorine. Fluorine is 4. So this one is polarized to this way. Hydrocarbon electron is more condensed on the carbon area. But with a lot of the fluorine, electron was moved out to the outside, this side. And this material has very unique properties, and they are not mixing with aqueous or even organic. It can form third layer or even fourth layer, different layers can form. different properties of materials they can form. Not only hydrophobic, hydrophilic. So high fluorinated materials, they have a special name. What is it? You know the name. I'm sure you know the name. Teflon. Teflon is the basic material of polyfluorinated materials. And another phase, as we know, ionic liquid. They can form different layers. So world is not so simple, but in organic chemistry, we have a tendency to distinguish those materials between polar, non-polar, hydrophobic, hydrophilic, depending on those separation power. Okay, so this is the table of electronegativity. By looking at this table, by looking at this carbon 2.5, now organic molecules, the simplest molecule is CNH, but now today we are going to learn about by adding oxygen. And not many are the element to be used. Maybe next one, maybe nitrogen, and sulfur, and maybe phosphorus. Then maybe all. Majority of 99% of organic molecules we are managing. Now the main issue is how they can interact each other and then change its forms. But anyway, if you look at those main molecules, this is highest electronegativity, and oxygen may be next, and nitrogen and halogens. This is maybe top over here, and then slightly decrease. So this is good to know. Electronegativity wise, F, oxygen, nitrogen, and halogens. But altogether, all of these are the molecules. You have learned a little alkyl halide, but any of these hetero atoms, carbon wise, carbon is always electropositive than those at the heteroatoms. Right? So that means always carbon was partially positive. These guys were always partially negative. Carbon was always partially negative. That means that carbon position is they need more electron. That means that position is electrophilic. That is a target of a nucleophile. That nucleophile's nucleus is a carbon nucleus. But carbon itself is electron division. That is the center of reaction for the SN2, SN1 type of reactions. Is there any way to change that character? Right now, carbon is always positive in the natural structure. Can you change it into negative? How? Here's the hint. How can you change carbon into negative? Okay, CH. Problem of CH is reactivity is very low. The difference between 2.5 2.1, electron is a little more shifted to hydrogen, but that difference is not much. It's more closer to covalent body. Means maybe 20% shifted, 30% shifted. Now comparing 2.5 to 4, that can make maybe 70% shifted. That make a hetero polarized bond, right? CH bond is not that polarized, slightly polarized. What is the other possibility? Metals. If you look at those metals, metals are even less than 1. If there's any chance, now this is actually the classification, the criteria, why we call these materials metals. Okay? Metal has its own property, metallic property. What is it? They have shiny surface because of free electron. And they tend to give out the electrons, reducing. Because they are oxidized, they give out the electron. Right? And electronegativity is very low. They are giving electrons. If there is any way we can connect this carbon with metal, now charges are changing. Metal is anyway prefer positive charges. Carbon becomes negative. Then this one you can call carbocation character. Right? Partially with the positive charges. Then upper one, that one, this one can be carbocation character. Nucleophile always electron rich, right? They need to carry the electron to attack the electrophilic conditions. Now, always it's carbon center. So far, we learned they are electrophilic center. But now we have a chance to think about possibility of using carbon as nucleophile. If you can connect that with the proton, okay, that kind of examples we already have learned last semester. 다 기억 못할 테니까 오늘 그런 예를 보도록 하죠. Now, if you think about the simple hydrocarbons, we have a lot of crude oils. Now they have different lengths, and depending on those conditions, maybe the distribution may be a little different. And then I just draw saturated hydrocarbon, but there may be some unsaturation may happen, and maybe some benzene can be incorporated here too. And crude oil is mainly this kind of non-heteroatom containing hydrocarbons. Hydrocarbon usually reactivity is very low, very boring molecules in a sense. Usually the only way to change this into usable molecule, we needed to give high pressure, high temperature to break down. Their breaking down is a homolytic cleavage. You apply more thermal energies, and they vibrate further and further, and they break, generate radicals. Because it's even, CC is the same, CH is not much different. And thinking about C plus, H minus, or the opposite way, the chance is low. So that's why usually the breaking is usually radical reaction. Require very high temperature, the high pressure for boring reactions, and difficult to predict the product. So always they, even after refinery or the process, they may change this distribution shift, but it may not change much of those chemical reactions. Exactly the same reason. Our body is mainly made of carbon-based organic molecule, but we cannot handle this molecule. That's too simple. We cannot drink crude oil. If we can, then maybe 세계 식량 문제는 많이 해결되겠지. It's a high energy containing material. That's why it's a good material for fuel. It has high energy in there. But we cannot take it because our body is too isolated from them. We need some clues to handle, and that clue, most closest molecule, is fatty acid. Long hydrocarbon, but we need some handle at the end. Carboxylate is the choice that we took. Using this one now, we can take and then move on to the next step. How? Cleave 2 by 2 and then use that as an energy source. That's why fatty acid, the first product from the photosynthesis is glucose. Right? That's a carbohydrate. It has a lot of oxygen in there. It's a partially oxidized product. Energetically, this one is more energy in there. Fatty acid is almost double, a little more than double than carbohydrate by weight, because it has pure hydrocarbons, majority of them. And only one side, we need some kind of group which we can use. That group we call functional group. That's totally from our view of the point. Using that 작용기 functional group, we can do with this group for something, changing that or the converting into more useful material and things. So this is common material we use closest to crude oil. Okay? For that group, now we can think about the role of oxygen. Maybe first the product may be alcohol. Long hydrocarbon, we add oxygen somewhere, and then they can start as a functional group, functionalize the molecule. Functionalized means something we can use. That means crude oil is not functionalized, it's boring, just a fuel. Functionalized, and then this alcohol that we are going to learn, this can be oxidized, aldehyde form, and this aldehyde form can change its form into phenol form. Okay? And then even if another hydroxyl is attacked here, it can form this kind of a dihydroxyl the intermediate. And this is aldehyde hydrate or acetal, we call. And this kind of product may be formed, but forget about this for now. The alcohol, and first oxidized product is the aldehyde, and then further oxidized form is the carboxylate. So this one is some reaction that we can utilize. This part we are going to learn later. Today we are going to focus on alcohol. First oxygen and alcohol. Now, any kind of hydrocarbon or carbon-containing materials, maybe even charcoal, carbon is 철광 말고 charcoal 뭐라 그러지? 거칠에서 철광석이랑 뭘 수입하는 거지? 석탄소는 뭐라고요? 소타라는 거 뭐지? Anyway, carbon itself or partially the oxidized carbon monoxide, that's also reactive species. Industrially using this and then hydrogenated here, or carbon plus water. And then we can form maybe simplest alcohol like the methanol. Or next one is the ethanol. Then we can think, starting from this double bond, then if you add water, this reaction we call hydroxylation. And then one hydrogen added and the other side, the OH is added. Then this one can form ethanol, which is quite familiar to us and also in a sense is body friendly material. Methanol we cannot take, it's very toxic. Ethanol we can drink. Propanol even is the dangerous. If we take a lot then we cannot manage. Ethanol is the only one we can take quite high concentration. So by concept, you already have learned one of the chapter of the last semester, alkyl halide, chapter 11. Alkyl halide already we learned a little the functionalized the molecule. That one is also not usually naturally occurring. That's also synthetic molecules. But anyway, if you have, let's assume somehow we have halogenated hydrocarbon, then that can be good starting material. Then alcohol generation is straightforward by using this hydroxide nucleophile and attach here and remove one bromide and we can form alcohol. If you have the alkyl halide, then that's a good precursor for alcohol. Then this reaction we can generally this reaction we can call this is nucleophilic substitution. We change it halide with OH minus. And when you learn about this nucleophilic additions, actually this reaction is also possible. There was alkyl halide. Another halide came in. And then if you react with this, it's exchange reaction, halide with another halide. Now, if you think about this reaction can be, depending on the conditions, this can be equilibrium reaction. Right? Maybe reactive-wise there is a little difference. And depending on the solvent and reaction conditions, sometimes chloride is more preferred, sometimes the bromide is better, but in general, this one should be, if you draw here, I cannot draw here. If you draw here, this is equilibrium, like this, most likely. But the first reaction, if you look at alcohol formation, that reaction practically is not equilibrium. That reaction is only goes to this way. Why is it? What's the big difference? It's the same SN2 reaction. And nucleophile is just a change here. And why the first reaction, that SN2 reaction is not equilibrium? Why is it? Reactivity of OH minus and some of those the halide. Nucleophilicity wise, sometimes halide wise, chloro, bromo, iodide, which one is more reactive? Usually reactivity wise, if it goes down, bigger one is more nucleophilic, more softer, and it has more moving electron, then they can attack carbon better. So reactivity wise, this is kind of a hard nucleophile, it's a tight, and reactivity of nucleophile wise, sometimes halide is even better. Then reactivity side, nucleophile reactivity side may not be main reason. Then, which one? Electronegativity. Electronegativity can define maybe basicity, and in general, stronger base has a stronger nucleophilicity. That's true, but that's also, depending on the conditions, that may not be the determining the factor. if you want to see the reaction goes to one side, always reacting species, reagent versus product. Product is more stable or happier in that environment. Then if you draw the reaction profile this way, right? This is more stabilized. If you push the reaction to that direction, this control, what do you call? There's a two kinds of control, right? Reaction. Kinetic control and thermodynamic control. This control is a thermodynamic control. Kinetic control is you need to control the temperature and the condition very carefully. You capture that semi stable status or metastable status and then isolate them. That's kinetic control. Thermodynamic control is a thermodynamic law, second law. It goes to always more stable status. That means comparing to reactant, product should be stable. Right? That's the way you push the reactions to the product direction. Now, if you think about the reverse reaction here, the problem is OH minus is not stable. That means it's more energetic. Then, in comparison, Bl minus or the Cl minus, both of them are conjugate base of strong acid. Means they are much more stable as is. That's why this reaction is kind of reversible in both sides. This reaction, this one is too reactive. And if you push out this reaction back, then you need to generate the species of here. That species product is living group. So the living group's stability determine whether that reaction happens or not. This OH minus is not good living group. But there is a way how we can push that reaction to this side. How can you do that? Okay, let's come back to that with the question later. Now, if you compare alcohol with the other materials, alcohol is a kind of partially organic molecule and partially water-like molecule. Right? One side OH, the other side hydrocarbon. It's like a Banyan-Bansu. That's why water has protonation, proton accepting property. This alcohol is also almost doing the same thing. That's why if you react with acid, it can take up to one proton. And if it meets with a base, then it can donate one proton. Then the property would be quite similar, and phenol may be also similar the way. Water carries daily exchange that between them. But alcohol carries with another solvent or maybe with other material together. Phenol may have the same thing, but phenol has a little more stabilizing power. That's why this donating is even stronger. So that's why if you look at those acidity of the profile, the water can be standard here. Water is approximately 16. Water's pKa is 16. Then alcohol, if you look at around here, ethanol, others is similar, you can expect. Slightly different, but around range of 16. Water usually we believe that's neutral, right? That's neutral. We don't call water as acidic or other basic. Now, if you look at phenol, phenol is approximately pKa 10. In comparison to water, pKa 10 is slightly acidic. You can think pKa 7 may be the standard. If one material has a pKa 7, what's the meaning? Usually the neutral conditions we call pH 7 is neutral, right? Then pKa 7 may be good standard. That should be neutral. If one material is pKa 7, physically what does that mean? 이것도 일반 과학 수준의 질문이긴 한데 이것조차도 어려우면 머릿속에 깔끔하게 잘 안 나오는 경우가 많아요. Carboxylic pKa 3,4. We call it weak acid. Phenol pKa 10. That's even weaker acid, but we call it acid. Water, alcohol, pKa 16. That's neutral. If it goes higher than that, pKa 20, then it can be basic. Now, pKa7 material, if we have, what does it behave at pH 7 solution? Half of the material donate the proton. Half protonated. Half donate the proton. That's pKa7. That means it's a quite strong acid. pKa6, then at pH 7, 10% of them is neutral, 90% approximately, 90% protonated, deprotonated. pKa4, then 5, 6, 7, 1 out of 1,000, they stays neutral, and the other 99.9% they donate the proton. That's a carboxyl acid. It's quite strong acid. pKa10, 8, 9, 10, 1 out of 1,000, they donate the proton. It's not very strong, but that's also kind of an acid, the proton source generator. That's why pKa10, the phenol, we call it as a weak acid. Okay. Now, if they have electron withdrawing, the electron donating group, then it becomes weaker acid. Because electron donating effect, we learned alkoxy amino groups on benzene, they donate electron, then, and the result of after donating, it becomes the anion. That anion can be destabilized. So it's not preferred. That's why it becomes a little weaker acid. If it has a strong electron withdrawing group like nitro, it becomes how many fold? Almost 1,000 times stronger acid. This becomes almost a 7. Nitrophenol is, if you put that molecule into the water, half of them protonated, half of them deprotonated, half and half. It's quite strong acid because this electron withdrawing other part is stabilizing the alkoxide. So based on this, we can assume that starting from any kind of alcohol is pKa 16. Now, if there's electron donating group, then it can be weaker. Electron withdrawing group, it can be stronger acid. Make sense? CF3 with this electronegativity withdrawing, alkyl group is weak, but it's a donating effect. We talked last week in benzene reactions. Alkyl group is a weak electron donating that makes the acid a little weaker. Now some reactions. With alcohol, now let's think. With alcohol, if you add metal. In water, if you add the sodium, what happens? Explosion. Because the proton accepts the electron very quickly, it generates the hydrogen gas. Same thing, in alcohol, if you add metal powder, potassium or sodium, magnesium, the first reaction is this proton reacts first with this metal and it generates the hydrogen. Among chemical reactions, the fastest reaction is acid-base reactions. Why? The reaction is intimidated by proton, right? Proton is the lightest element, and that's why moving speed would be fastest. That's why reaction is quite fast. Similar things here. In this case, even faster maybe, electron is moving from metal to hydrogen at the proton, and this reaction is quite fast. Water, alcohol, same reaction you may expect. If you add metal powder, this reaction happens. Now, strong base, but this base is a little funny base. It's not sodium hydroxide, sodium hydride, H minus. H minus meets with H plus. It's also meet together and generate hydrogen gas. And the result is this, but the alcohol is methylated. It behaves like a base, but more reactive base. Okay. And if they meet a strong base, alcohol is weak the acid, but with a strong base, it can bond this kind of the methylated bond too. Now this one, if you look at this example you have learned before, what is the name of this reagent? Grignard reagent. How do you make this reagent? Anybody remember? Grignard reagent. How do you make it? 아무도 기억 못하는 걸까? 아니면 그냥 겸손한 걸까? How do you make a Grignard reagent? You start with alkyl halide, and here you add magnesium. Originally, this side was electropositive, and this side was anion character. Now, this magnesium was inserted in between. Same negative. Now this one becomes negative. This one is positive. That reaction is also oxidation and reduction. Which one is reduced? Which one was reduced? Carbon was reduced. Originally +1 becomes -1. Originally carbocation character, it becomes carboanion. And which one is oxidized? Magnesium was oxidized as usual. Metal powder always giving electron. Okay? Magnesium can give 2 electrons. So one was given to chloride, the other one given to the carbon. So 2 electrons was moved. That similar reactions can happen with a single electron giving metal 2 with a lithium. But in this case, you need 2 lithium. Then the product is alkyl lithium and lithium chloride. In principle, this is the same reaction with the metal, and it forms carbanion character here. That carbocation can act as nucleophile. Okay? So we just changed the electron density from positive to negative reactions. And this reagent is also a very strong reagent. And if this meets with a proton, something you don't want, like water, Grignard reaction, if you have a small moisture in your reaction, then that proton reacts with this, that's the alkyl group first. Then end product, this CH3 minus react with the proton, it forms methane. Usually that's not the reaction you want, right? Grignard reaction, as you can see, is maybe expensive and difficult to make, and water sensitive. Small amount of water or alcohol in there, proton source, it just destroyed the reagent, making simple hydrocarbon. Who wants to make a solute out of expensive silver reagent, right? So that reaction can happen with the Grignard reagent. So some examples we have seen. Now, phenol is weak acid. That's why it meets with the base, and it can form this kind of a deprotonated form. And the reason of the stability of the acidity of a phenol compared to alcohol, after it forms this negative charge, phenol has more chances to distribute out that extra charges. Alkyl alcohol is more condensed charges here. That means that it's still reactive. More reactive means that it's still unstable. That's why it does not like this one. Phenol is more stabilized. Now with the electron withdrawing group, that's even better. Stabilizing that anion further and further. Electron withdrawing carbonyl or nitro is even better. By drawing this kind of a resonance structure, you can form many other resonance structure. It's a little more cumbersome to draw all of them. Let's say nitro has a stronger electron withdrawing effect compared to the carbon groups. Okay. So nitrophenol nitrophenol case we have seen, it has approximately pKa7 range. Now, this is some reactions, how we can prepare for the alcohols. Which one we have seen so far? Maybe starting from alkene, hydroxylations, by adding hydrogen and hydroxy here. The others we didn't learn yet. Alkyl halide we have seen. Alkyl halide now it forms with react with the hydroxide, it can form alcohol. So some of these reactions, it can go this way or the opposite way too. Today we are going to see some examples of how we form alcohol. Next class, we are going to see how this alcohol reacts to make different products. Okay. Mainly this week is all about the alcohols. Property a little is partially organic but partially water-like. Means it can deprotonate or the protonate partial part, and then some of those reactions. This one you have learned in chapter 8. Addition to the alkene, and two examples you have learned. One is hydroboration. Hydroboration, that hydro means a hydrogen. pH3 is broken into two, hydroboration. Okay. The other reaction was using mercury, and then you learned in this case, hydroboron was added, but in this case you call this reaction oxymercuration. Oxygen and mercury is added. And this the reaction, there was some rule you have heard, I guess, Markov-Dikov rule. That addition site, the hydroxyl addition site wise, this is actually two-step reactions. This boron site is oxidized by hydrogen peroxide later, and then hydroxyl group is attached here from the same side of boron. Okay. First reaction is similar to hydrogenation, metallic hydrogenation, two hydrogen added together. Same thing, hydroboration is also this H and this BH2 moved together to the same side. And then oxidation happened only on boron side. That's why this hydroxyl group is on the same side with this product. And the result wise, in this case, Markov-Dikov rule says new hydroxyl group addition happens to more substituted position. That's why oxymercuration is Markov-Dikov product. Hydroboration was an anti-Markov-Dikov product. Name is not so important, but depending on those mechanisms, through what mechanism it formed this product, and this product is important. Right? This case, hydrogen and the boron was added the same side. This case, it was the opposite. It forms different intermediate, cyclic intermediate, and the hydroxyl was attacked from behind. That's why those two products was formed, different additions. One is a syn addition on top, the other is anti-additions. Okay. If it's not clear, then review those chapter 8, 8-4 and 8-X7, I guess. Okay. 이런 거 짬짬이 하나씩 나올 때마다 부족했던 부분 찾아서 외우면 1학기 거 다 공부 안 해도 여러분들 쫓아갈 수 있어요. Okay. This is one reaction. Using alkene, and we add hydroxyl groups. So I'll show you examples in the main text, so you can check. Another other case is reduction reaction. Usually the alcohol, if you start with the alcohol, it can be oxidized, moving to ketone or aldehyde, or the carboxylate. We can convert back onto here. Then this reaction we call, this is oxidation. Then this reverse reaction, that should be reduction reaction. To do this, you need, if you think, nucleophile addition here, this is electropositive, electronegative, this is nucleophilic side. Attack happens here. We need some kind of H source, but that H may not be proton. That H should be electron-rich H. That kind of the hydrogen we call hydride. Okay. Hydride is anionic, nucleophilic hydrogen of the material. That's H minus with the 2 electrons like this. So conceptually, if we have a hydride, this hydride can attack here and then push these electrons up. it draws this way, but actually it should come from the behind. Electron movement should happen together. Moving past here, push, that's this by electron moving same direction. So it comes here and push it out. That's one step. And then this one coming back, it can push it out, then reverse reaction. Or if it's finished by catching another proton from outside here, then reaction finishes. This kind of, conceptually, this is a hydride, then real reagent for this. Okay, anyway, before we go there. So if it is aldehyde, it forms primary alcohol. If it's a ketone, then it forms secondary alcohol. It's obvious. And the reagent here is this kind of reagent. Sodium borohydride is one case. Let's start here. This is metal, but main source is here, BH4. And it has 4 H- sources there. Boron is more electronegative, electropositive than hydrogen. That's why in this special case, hydrogen has a more electron that can act as H- hydride. Okay. Now, if you react with the sodium borohydride, H- attack here, then you can form primary alcohol like this. Ketone, same way. Using this one, then secondary alcohol can be formed using hydride reagent. Now, if you have two reaction sites, now previously we have seen metallation reaction, the hydrogenation reaction using the metal catalyst. Then hydrogen reaction may happen here. But in this case, H- is polar material, electron-rich polar material. It attacks more electropositive site. That electropositive site is this color. Then it attacks here and go here. Now we have a little different reagent. Comparing to sodium borohydride, lithium aluminum hydride. Actually, chemists tried to change every position here. Sodium aluminum hydride, lithium borohydride, different combinations. This is all alkali metal. This is also the family tree, the groups. So it can be exchanged. They found that if this goes smaller, that's more reactive. If this goes bigger, that's more reactive. So this is a combination of a stronger one. This is a combination of a weaker one. So as a summary, this one is a little weak reagent. This is strong reagent. Okay. So if it is not necessary, then using sodium borohydride is a little milder condition. Lithium aluminum hydride is even stronger, more moisture sensitive, more difficult to handle. You need to have low temperature kind of things. Okay. But the choice is, if there is aldehyde or ketone, simple one, sodium borohydride is fine. If it's a little more reactive, the less reactive one and difficult one, you need to use lithium aluminum hydride. Especially the represented case is carboxyl acid and ester. Then sodium borohydride is not strong enough. You need to use lithium borohydride. Now the product, if you look at here, carboxyl acid. Let's check this one first. First reaction, hydride attack here. Very first reaction would be reaction with a 1 H- with a H+, right? Alcohol even can react with hydride. Then carboxyl acid proton is more amount of a proton. That's why first reaction will be one hydride will be removed by this proton. Second reaction is hydride attack. Push this out, remove one. Third one, attack again and push it out and finish up the reactions. That means at least 3 hydride is required to reduce carboxyl acid. Ester, first hydride attack here, push it out. Second one attack and push out. At least 2 hydride required. Okay. So using this the reagent, then if you look at those acid and ester, now acid here, even though there is double bond here, that double bond is non-polar double bond. H- does not prefer that. This is maybe target for the metallic hydrogenation, not target for the hydride. Hydride attack this position and push out and then reduce and then finish up into alcohol. ester also, this one attack here, same way, this one is not attacked. And only this side is attacked, push out, push up, and then finish up with the alcohol. Okay. Now, if this is simple ketone, it doesn't matter. Either one you can use sodium borohydride or lithium aluminum hydride. Both of them can work. But acid and base, the acid and ester, you need a special case. This one doesn't make sense. Okay, we covered a little of those reagent, the reaction today. 조금 많으니까 남은 거는 다음 시간에 같이 하도록 합시다. Today we studied about alkyl halide to alcohol, and then reduction reaction from ketone or aldehyde moving to this reaction, or carboxyl acid or ester with a little stronger hydride reagent, lithium aluminum hydride. This case could work with the sodium borohydride, and starting from the alkene, hydroboration or oxymercuration reactions can generate this. 오늘 아침에 수업 준비하는데 누가 찾아와서 이런 질문을 했는데 교과서에 그런 문제가 있었고 이걸 가지고 구조를 그리라고 해서 이렇게 그렸다는 거지. 그리고 그 다음 문제를 봤더니 이름을 이걸 매기라고 하는데 이걸 기준으로 해가지고 이거 이름을 매기면 이름을 뭐라고 매겨야 될까? 여기서 질문은 넘버링이야. 넘버링을 어떻게 하면 좋을까? 기준을 정해야 될 거 아니야. 처음에 이걸 보면 기준을 그렇게 어떻게 정한 거지? 알파벳으로 했을까? 알파벳인가? 저 기준 정할 때 알파벳으로 하는 거지. 알파벳으로 하는 거야. 그런 거 같은데. 오래돼서 잘 기억이 안 나는데 수업 20분 전에 찾아와가지고 근데 생각에는 그때 이게 엘리먼트의 아토믹 넘버가 큰 거가 더비다 이렇게 생각을 했는데 그래서 그거가 좀 더비고 알파벳인지도 모르지. 여하튼 룰을 하나 그걸 정했다고 치면 이건 메틸이니까 알파벳으로 했다고 치고 1 클로로 3, 5 이렇게 적었다고 쳐. 그리고 벤젠 이렇다고 치면 이건 이름이 뭐라야 돼? 번호 다시. 그런데 뭐 저 솔루션에 이렇게 돼 있을 때는 거지. 이게 왜 맞지 않냐? 어느 기준으로 보더라도 짝이 안 맞잖아. 찾아보니까 솔루션 틀렸나? 이렇게 쓰는 게 맞아. 그래서 그건 내가 다시 찾아보겠는데 처음에는 아토믹 넘버가 큰 거를 위주로 한 거가 맞다고 생각했거든. 그렇다고 생각했는데 알파벳 이름 순인 것도 어디가 있었던 것 같아. 그거는 내가 다시 확인해보고 알려주겠는데 솔루션이 이게 틀려서 원성을 준 것 같아. 그래서 여기에 좀 자, 여러분들이 나한테 찾아오는 시간이 오늘 아침 같은 시간 내가 사실 좀 바쁘거든. 그래가지고 노트 정리 마지막으로 한번 하고 여러분들한테 1시간 전에 올려놓고 나서는 수업 시간에 어떤 순서로 어떻게 할까 뭐 이렇게 정리하느라고 아침 시간 좀 바빠. 그래서 내가 오피스하고 준 거는 목요일 오후 수업이 끝나고 나서 2시까지 사실 그 시간에 수업 있는 친구들은 뭐 따로 해서 잡으면 좋은데 그 시간에 내가 제일 여유가 좀 시간이니까 그 시간을 활용해 주면 좋겠고 급한 거는 뭐 언제라도 오면 좋기는 한데 아침 시간은 내가 좀 바빠. 그러다 보면 내가 수업 준비할 때 노트 준비를 막 하다가 여러분들한테 나눠주는 거는 다 있는 걸 주고 내가 수업할 때는 중간중간에 가려놓는 거 이런 거 하잖아. 가려놓는 거 다 했는데 효린이가 왔다 가는 바람에 그걸 잘못하고 세이브해버려가지고 그걸 다 날려먹었어. 수업 들어오기 직전에 내가 그 정도로 들어왔는데 가능하면 시간을 그렇게 가져갔습니다. 오케이. 자, 오늘 수업 시간 좀 끝났고 아직도 우리 알코올이랑 페놀 반응 다